Pluto had it coming from the beginning. It was never really belong. Pluto's orbit crosses that of another planet. That's no kind of behavior for a planet.
Pluto had it coming from the beginning. It was like it was never really belong. Pluto's orbit crosses that of another planet. That's no kind of behavior for a planet. Pluto, a far-off and baffling smaller planet, was once an individual member of our solar system's planetary family. However, later, alarming declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into the spotlight with a stunning disclosure. They suggest that this frosty world is on a potential crash course with Neptune. But how could this happen, and what might be the outcomes of such an enormous event? Are we seeing an interesting cosmic phenomenon, or is there something else to this looming infinite crash? Join us as we investigate the potential outcomes of a Pluto-Neptune collision. Pluto, a previous planet that was downgraded to a dwarf planet partly due to its curious orbit, remains a subject of interest and study in the cosmic community, according to recent predictions by leading researchers. Pluto's trajectory is perilously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the warning of a potentially dangerous crash between these two planets that could be an immense threat to Earth. But how is such an event even conceivable? Pluto's journey around the Sun is unlike any other planet in our nearby planetary system. It requires a stunning 248 years to complete a single orbit. This means that since its discovery in 1930, it hasn't even completed one full revolution. However, the interest doesn't stop there. Pluto's path is marked by its highly elliptical shape, diverging entirely from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination. Calculated at 17 degrees to the ecliptic plane, the path Pluto follows is much steeper compared to the other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its convergence with Neptune's. For around 20 years in each orbit, Pluto actually draws closer to the Sun than Neptune, resisting what we might expect from their positions in the solar system. This leads to the natural question, why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers struggled to grasp its unique path. Unlike the other planets whose orbits lie somewhat near the ecliptic plane, Pluto's orbit stood out with its steep inclination and eccentric shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of celestial mechanics. The three-body problem in space is about figuring out how three objects in space like Pluto, Neptune, and the Sun move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on one another. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all cooperate in a complicated way. Terms like asymptotic libration, scope libration, and VSK oscillation are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is a kind of libration regarding Pluto and Neptune. This term means that whenever Pluto crosses Neptune's orbit, its position is always at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from colliding. Scope libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, offering an extra layer of protection from potential impacts. Another critical factor in this situation is the VSK oscillation. This is named after three researchers, Vyaskapel and Kay, who studied how things move in space. It's about how three space objects like Pluto, Neptune, and the Sun pull on one another with their gravity. This pulling influences how they move. In Pluto's case, the VSK helps us understand why its path around the Sun is so strange despite the apparent chaos. This oscillation helps keep Pluto's orbit stable for an extraordinarily long time. The VSK oscillation shows that even though things in space may seem wild and random, certain patterns and rules keep everything in place. All of these parts help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or stray off course. This three-body problem helps in understanding how these orbits change. Due to the way space objects pull on one another, studying this helps us learn more about Pluto, our solar system, and distant stars and planets. Mathematical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is actually turbulent with minor deviations in initial conditions leading to significant differences over millions of years. However, these unusual properties of Pluto's orbit have been found to maintain stability over incredibly long time scales, effectively keeping the chaos under control. Recent computer tests have helped us understand how the giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a special relationship with Pluto, wherefore every 2 orbits Pluto makes around the Sun, Neptune makes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only one helping. Jupiter's gravity also plays a large part in protecting Pluto's orbit. What's more, Saturn helps overall too. These tests show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a steady path for an extremely long period, possibly even billions of years. It's as if Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely in space without running into trouble. These peculiarities are vital in the larger context of the universe for maintaining the order and consistency of celestial bodies' movement. Without these components, the solar system, as we know it, would be a place of far greater turmoil and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable orbits, leading to a domino effect on other celestial bodies. For Pluto, particularly with discussions about it possibly colliding with Neptune in the future, understanding its orbit is essential. This gives us a clearer picture of the solar system's dynamic nature. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of balance through the complex interaction of gravitational forces and orbital mechanics. It also shows the importance of constant observation and study of these phenomena to better grasp our place in the universe. Investigating the depths of space often leads us to confront the eccentric nature of celestial bodies, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is clearly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can significantly change its long-term orbit. Using virtual simulations has been incredibly helpful for researchers to figure out how Pluto moves in space. These simulations use intricate math to mimic how Pluto, along with other space objects like Neptune, pull on one another. By adjusting small details in the simulations, astronomers can see how even tiny changes can make a big difference in where Pluto ends up. In the late 1980s, these simulations showed something really interesting about Pluto's orbit. Despite having mechanisms like asymptotic and scope libration to keep it stable, its orbit can still be wild and unpredictable. If you start with even a tiny difference in where Pluto is or how fast it's moving over many years, its path can end up looking very different. However, despite this chaos, Pluto's orbit remains stable for a long time, billions of years. This means Pluto's journey around the Sun has a kind of order to it, even though it seems all over the place at first. Predicting large events, especially when they involve chaotic orbits like Pluto, presents huge challenges. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While mathematical simulations provide a strong tool to understand and predict the future behavior of celestial bodies, they also highlight the limits of our predictive capabilities. These models depend heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight mistake or distortion can lead to drastically different outcomes, making precise predictions a daunting task. Furthermore, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made huge strides in understanding space, the case of Pluto reminds us of how our knowledge of the universe still remains limited. Understanding the gravitational influences of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have sweeping effects, influencing the stability and trajectory of other bodies within the system. So why are prominent astrophysicists only now raising concerns about a potential crash between Pluto and Neptune? Despite all these complex forces working to prevent such an event from occurring. Neil deGrasse Tyson, a renowned astrophysicist, offers a unique perspective on the mysteries of our solar system, particularly the captivating case of Pluto. Tyson, known for his role in the renaming of Pluto from a planet to a dwarf planet, offers insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the unexplored reaches of space. Tyson's position on Pluto's renaming is rooted in the ever-expanding knowledge of our solar system. He sees the renaming not as a downgrade, but rather as a necessary adjustment to our growing understanding of the many bodies orbiting our sun. Tyson's approach to celestial mechanics is one of continual learning and adaptation. He views the intricacies of Pluto's orbit, as well as its interactions with Neptune, through a lens that recognizes the unpredictability of space. He suggests that these interactions, while unlikely to lead to immediate catastrophic events, are part of the greater picture of cosmic chaos and evolution that is constantly unfolding. In conclusion, the possibility of Pluto and Neptune crashing into each other in the future serves as a striking reminder of the complexities of celestial mechanics. The fact that Pluto's orbit is both stable and unpredictable at the same time highlights the fragility and power of space. What might seem to be a chaotic or unstable system is in fact governed by delicate balances that scientists are still working to fully comprehend. Please subscribe to our channel, Digital Discoveries. Like and share the video with your friends and family members. Thank you so much for watching the video and supporting us. We appreciate your continued interest, and we'll see you soon in the next video.